Hello, students. This is Mr. Coker, and we have a snowstorm, and it has kept us from getting together as a class. So the test that was supposed to be this evening will be on Tuesday. So the test is postponed till Tuesday. I'd still like to get through some Chapter 13 notes, though, so that we don't fall behind and have to scramble to try to catch up by the end of the semester. So this is considered your lesson for Thursday night, February 3rd, and the topic is the start of Chapter 13. So this will not be covered on the test on Tuesday. This is instead the notes for the next set of chapters that lead into Exam 2, which I believe is right before spring break. So I will be posting sometime before Tuesday the homework from Chapter 13 and the 20 questions that we'll be working on for Chapter 13. So get those announcements out of the way. I'll also mention that when I post these videos on YouTube, YouTube gives you the option of speeding up or slowing down the videos. I think that's a very good tool for your study purposes. If you think I'm talking too slowly or I'm going too slowly, I'm doing something you already know about, feel free to speed up the video and move on to the parts that you need more focus on. If you think that maybe I'm talking too fast or going too fast, you can always use the little scroll thing at the bottom to go back and listen again. In fact, I do recommend that. As many times as you need to listen to these notes to get a full grasp of what we're really getting into here, feel free to listen more than once. Also, feel free to like, comment, and subscribe to my new YouTube channel, Terry Coker FCC. So without further ado, let's get into Chapter 13, Acids and Bases. So this follows up Equilibrium, Chapter 12, very closely because acids and bases equilibrium is a very important aspect of their existence. So I know we've talked about acids and bases in first semester, but that was just a very slight coverage. We're going to go much deeper in Chapter 13 and 14. But in these chapters, we're going to be focusing a lot on the equilibrium of weak acids and weak bases. So keep that in mind that we're going to do a lot with equilibrium problems and equilibrium constants. A little bit today and a whole lot more on Tuesday and Thursday of next week. So Chapter 13, Acids and Bases. It has 12 sections. We hope today to get through the first four, 13.1, 13.2, 13.3, and 13.4. So we're going to learn enough to be able to calculate the pH of strong acid solutions. Looking at the first section, let's just talk about what are acids and what are bases. Now the concept of an acid has various definitions depending on which scientist you follow. The Arrhenius concept is the one that's usually taught in introductory chemistry at, say, the high school level. It's a definition of acids and bases. It works very well for the aqueous solutions of acids and bases that we usually deal with in a chemistry classroom. Arrhenius said that acids are molecules that produce hydrogen ions, or H plus ions, when they dissolve in water. Bases are molecules that produce hydroxide ions, OH minus ions, when they dissolve in water. So keeping in mind that acids make H plus, bases make OH minus. You put an acid and base together, the H plus combines with the OH minus to make H2O. So when acids and bases react, they neutralize each other and become neutral water. This is a good definition, but it is a bit limited. It only applies to aqueous solutions, and it only allows for bases that produce the hydroxide ion. A bit more broad definition for acids and bases is the one from 1921, the Bronsted and Lowry model. Bronsted-Lowry model. In the Bronsted-Lowry model, they focus on not H plus and OH minus, but just on H plus. And they call H plus a proton. They say acids are proton donors. Acids are molecules that transfer H plus to another species. Bases are the species that take the H plus. So bases are proton acceptor. Now this is going to be the model that we mainly focus on throughout chapter 13. So keep in mind that we won't be talking so much about the Arrhenius definition, but the Bronsted-Lowry definition. Acids are proton donors, bases are proton acceptors. So to take a look at how that might work in a typical acid dissolving in water situation. So HCl is an acid, hydrochloric acid. When it dissolves in water, the HCl, the acid, is going to transfer a hydrogen ion, H plus, to the water molecule, forming the H3O plus ion called a hydronium ion. And since it loses H plus, what's left over is going to be chloride ion, Cl minus. So we see the reaction here. The water molecule with its polar negative, partial negative oxygen is going to pull the partial positive hydrogen ion away from Cl minus and form H3O plus hydronium ion and Cl minus. So in this particular example, we would say the HCl, since it gives H plus to water, is the proton donor, so HCl would be defined by the Bronsted-Lowry model as the acid. The water, since it accepts the H plus, would actually be defined as the base. So here we see neutral water being defined as a base. So it's a little broader example. We wouldn't normally, in the Arrhenius concept, think of water as a base, but if it takes H plus from something else, it's going to be a base. So we sort of have different ways of representing this ion that is normally considered the ion of acids. First of all, Arrhenius would say the ion in question that represents an acid is H plus, and he would call it the hydrogen ion. A hydrogen atom that has lost an electron, H plus. Now the Bronsted-Lowry definition calls the H plus ion a proton. The most common isotope of hydrogen is hydrogen 1, which is constituted with only a proton and one electron. If you take that electron away to make the hydrogen atom plus 1 ion, all that's left is a proton. So it is in fact correct to call an H plus ion a proton. However, protons in water typically are not going to float around by themselves. Being small and positive 1, they're going to be very attracted to anything negative, and typically the proton will be attached to a water molecule to form a hydronium ion or a hydrated proton, an H3O plus ion. So really, when we're talking about water solutions, we're talking about hydronium, not really hydrogen ion. So you don't really have any bare H plus ions floating around. They're usually attached to water molecules to make hydronium. However, for the sake of a shorthand, H plus is actually a pretty good way of writing it. In fact, it's shorter than trying to write H3O plus every time. So typically what chemists do is they call the ion H plus when they're writing it, just to save themselves a few extra numbers and letters and signs to write. But in fact, H plus is really hydronium, and you might want to keep that in mind. So in general, let's just look at the generic acid dissolving in water reaction. I know we look specifically at HCl, but a typical acid we could call HA, and the A could be Cl minus, it could be NO3 minus if it's nitric acid. So whatever the H is attached to that's going to give H plus away, whatever the rest of that is, A, we'll just generically call it A because there is no element with symbol A. HA then is our acid, and when you dissolve an acid in water, it's going to give H plus to the water to form the base. Now notice the double-headed arrow here showing that the reaction can go forward and reverse. So let's first look at what forms when HA, the acid, gives H plus to the base water. You're going to form the hydronium ion, H3O plus, or if you don't want to write it all out, you can just say H plus. And you're also going to form A minus, which is what is left over when you take H plus away from HA. So the acid gives H plus to the base, and the base would be water, and the acid we'd just generically call HA. However, this reaction can also go in reverse. If we look at the reaction in reverse, it would be the hydronium ion giving H plus to A minus. So now in reverse, hydronium, H3O plus, is the acid, and the A minus ion is the base. Now, because the hydronium ion is related to the base water by just the only difference being the hydronium ion has an H plus attached to it, we actually think of the base water and the hydronium ion as a pair. The water is the base form, the hydronium ion is the acid form. And we actually call it the conjugate acid of water. Hydronium is the conjugate acid of water, and A minus is the conjugate base of acid. So if you think about conjugating verbs in language class, you have a verb like go, but then you conjugate it to form the past form of it, and you say went. Well, went is the conjugated verb go. Go is the verb, you conjugate it to make went. Well, in a similar way, HA is the acid. If you conjugate the molecule HA to make A minus by taking away a proton, taking away H plus, you make its conjugate base. We call it the conjugate base because, as you see in reverse, it actually acts as a base. So we've got some terminology here. We have an acid and a base on the left, but then on the right, we have that acid's conjugate base, and we have that base's conjugate acid. So a little definition here. Conjugate base is what you have left after the acid molecule loses a proton. A conjugate acid is what you have once a base accepts a proton. So when a proton is transferred to a base, you create that base's conjugate acid. And so two things that are related to each other by having the same formula, except one has H plus extra and the other one does not, are called a conjugate acid-base pair. So like HCl would be an acid, Cl minus would be the conjugate base. Water would be a base, H3O plus would be its conjugate acid. They would be water and H3O plus are considered a conjugate acid-base pair. So you can tell they go together, HA and A minus or H2O and H3O plus. They're similar formulas. The only difference is one of the two has H plus and the other does not have H plus attached to it. And so those two together are called a conjugate acid-base pair. So we're focusing here on the Bronsted-Lowry definition, and the Bronsted-Lowry definition looks at having protons donating and accepting. So back to our reaction, our generic reaction, HA plus water, double arrow showing equilibrium, H3O plus plus A minus formed. The Ka for this, we'll call it the Ka because A for acid. This would be the acid dissociation constant according to the book. I would prefer actually the term acid ionization constant because HA is typically a molecule, not an ionic compound. Ionic compounds dissociate. Molecules that form ions ionize, but that's just semantics. So the Ka here would be the products over the reactants, or H3O plus times A minus over HA. Notice we left out the H2O because it's a liquid. Liquids are not included in equilibrium expressions. Or if you want to write it in a more of a shorthand, you could say Ka equals H plus times A minus over HA. So this ratio of ions ionized as H plus and A minus to the molecules of HA that do not ionize, that ratio is called the equilibrium constant for an acid, or the acid ionization constant, and it's given the symbol Ka. So let's practice writing some simple ionization reactions for some acids. Our acids are going to be hydrochloric HCl, acetic acid HC2H3O2, ammonium NH4+, aniline ion C6H5NH3+, and the hydrated aluminum 3 ion, which would be an aluminum plus 3 ion surrounded in water by 6 water molecules. So starting with HCl, we would write HCl makes H plus Cl minus. The acetic acid, HC2H3O2, that would make H plus acetate. Notice I've taken water out of the formula just for shorthand purposes. I've taken water out because you could put a water on the left and make the H plus as H3O plus, but I'm sort of shortening things down here just to make it more compact and quicker. But keep in mind, I could have written HCl like back here. I could have written HCl plus H2O makes H3O plus Cl minus, but a shorter way to write it is HCl makes H plus Cl minus. Ammonium, take H plus away from ammonium, you get NH3. Notice the formula NH4 plus has one less H and it loses a positive charge when you take the H plus off of ammonium. So the ammonium ion actually acts as an acid, and we saw that in lab, if you remember in that equilibrium lab, that adding ammonium actually changed the pink phenolphthalein to lighter pink. It was actually moving it in the acid direction. Here we have the aniline molecule, C6H5NH3+. If you take H plus away from that formula, you get C6H5NH2. Now finally, the hydrated aluminum ion. This looks complicated, but just keep in mind all we're doing is taking H plus away from the formula. Al plus 3 is surrounded by 6 waters when the aluminum ion gets hydrated in water. If we take H plus away, we've got to take it from one of those water molecules. The aluminum ion pulling on that water molecule weakens the OH bond and makes H plus easier to remove. So let's just say we take an H plus off. What's left? Well, we still have 5 waters we didn't touch, so AlH2O5. But then one of the waters, by losing H, becomes OH, and then the 3 plus charge becomes 2 plus. One aspect of the Bronsted-Lowry model, which makes it more generic or more general and lets it cover more examples, is you can actually extend it to reactions outside of liquid water. You could even look at reactions in the gas phase. You may remember that reaction we were showing with the white smoke at lab on Tuesday was a reaction between ammonia gas and HCl gas to make NH4Cl solid. Well, you could actually look at those two gases coming together and make a solid as an example of an acid-base reaction, because NH3 has that lone pair on the molecule. H could attach to NH3 using that lone pair to become NH4 plus and then Cl minus. And if you have a positive one and negative one ion, they're going to attach to each other and make an ionic crystal. So we would actually look at this as HCl being an acid donating H plus to NH3 to form NH3's conjugate acid, NH4 plus, and HCl's conjugate base, Cl minus. And so there's an example of the Bronsted-Lowry model being extended to gases. Okay, moving into 13.2, let's talk about strong versus weak acids. So strength of acid is how far to the right does the ionization lie. See, in a strong acid, strong acids are assumed to be 100% ionized or virtually all ionized. You put the HA in water, it completely breaks into H plus and A minus. But there are really only just a few examples of strong acids. Over on the right, I have a chart: HCl, HBr, HI, HNO3, H2SO4, and HClO4. If it's not one of the strong acids, it's going to be one of the weak acids. And so there are actually a lot more examples of weak acids than there are strong. Typically, we use the strong acids a lot, but there are a lot of examples that come up in chemistry of weak acids. So in a strong acid, because the equilibrium lies far to the right, we consider the conjugate base of a strong acid to be very weak. Let me look at it this way. I like analogies. Pretend that you have a car that you would love to sell because you hate the car. It's the wrong color, you don't like the way it runs, it's just always been a problem for you. So you find a sucker who's willing to buy your car off of you. So you would be an example of a strong acid. You want to give that H plus away. You want to get rid of that car. You have a strong motivation to get rid of that car. So you found someone, a base, willing to accept your car. You found somebody willing to buy your car off of you. You've sold your car. You've got the money from your car, and you've become effectively a conjugate base. You've become, you've lost the car. You've transferred the proton, and so you are now a base because you no longer have that proton. You no longer have that car to sell. So as a strong acid, you were very motivated to give up your car, to give up your H plus. Now pretend that you've sold that car, and an hour after the guy drives off with the car, he shows back up at your door and says, "Hey, would you like to buy your car back?" I think it's pretty clear you don't want to buy your car back. You were highly motivated to lose that car. You are not in the market to buy it back. In the same way, a strong acid is strongly motivated to give up H plus and give it away to something else. However, once it has given up the H plus, it becomes a conjugate base, but it's a base that is not motivated at all to take H plus back. That particular base would rather not have the H plus than have the H plus. And so a strong acid yields a very weak conjugate base. The conjugate base of a strong acid is not really considered basic at all. So in the case of HCl, you would not think Cl minus would ever want to gain a proton. Once HCl loses its proton, it doesn't want it back. In fact, Cl minus would be a much weaker base than even water. Remember, water can accept H plus. Cl minus would not want to accept H plus. So in the reaction of HCl, get back to that one, water can take H plus from Cl minus, but once Cl minus forms, it won't take H plus away from even hydronium, which is something that actually has an extra H plus it could give. So strong acids are molecules that give away their H pluses completely. We can say to the first approximation, they give their H pluses away completely. Weak acids, on the other hand, are going to be ones where that HA plus water yields H3O plus A minus ion. That equilibrium is going to lie far to the left. It's not going to go very far to the right at all. Most weak acids are less than 1% ionized. In other words, most of your acid is still going to be the HA molecule. Less than 1% of that HA molecule is actually broken into H plus and A minus. The conjugate base then would be considered to be a stronger base than water. It will be a weaker, in fact, the weaker the acid, the stronger its conjugate base. So now go back to that analogy of selling the car. Let's say that you really don't want to sell your car and you're somehow manipulated into selling your car. You were very reluctant to give it up, but you did sell the car, and then you get the opportunity to buy that car back. Maybe a good analogy would be you got to pay your bills. You really like your car. You have to pay your bills, so you sell your car reluctantly. And then later, when you're back to being financially solvent, you find an opportunity to buy the car or the same kind of car again. So you lose the car, you become the conjugate base. It's like being a conjugate base. You've lost the H plus, but you're very motivated to get that H plus back because you really didn't want to give it up in the first place. The weaker the acid, the stronger the conjugate base. If we look at our generic form here at the top, HA plus water makes H3O plus A minus. Water is accepting a proton from HA, but then A minus is taking a proton away from hydronium. And so we've got the reaction going forward, which isn't going forward very much. We've got the reaction going in reverse, which is actually very strongly going in reverse. So who's the better base? Water taking H plus from A minus, or A minus taking H plus from H3O plus? A minus is better. The reaction to the left is stronger than the reaction to the right. So in summary, what we can say is that the conjugate base of a strong acid, something like Cl minus, is a much weaker base than water. But the conjugate base of a weak acid is a stronger base than water. So conjugate base of a strong acid, weaker than water, weaker base than water. Conjugate base of a weak acid, stronger base than water. Okay, so looking at strong acids and weak acids in water, just to pictorially give you, for the visual learners out there, the acid on the left, HA, if it's strong, all of the HA molecules break up into H plus and A minus. So you see that in the picture with the circles there. You also see it with the bar graph. HA completely becomes H plus and A minus. On the other hand, HB, we'll call it HB to distinguish it from HA, but it's just another acid, but now it's weak. Start out with all the molecules attached, and then what do we see? One molecule broken into H plus and B minus, compared to a lot of them that are staying together at equilibrium. So once you reach equilibrium, it only takes a few ions of H plus and B minus to let the reverse reaction catch up to the forward reaction of ionization. So at equilibrium, you've got a lot of HB and very little H plus and B minus. So this table kind of summarizes strong versus weak acids. Strong acids, large Ka value. The equilibrium constant is large because it lies far to the right, lots of ionization occurring. Weak acids, very small Ka. Mostly this equilibrium lies to the left. At equilibrium, the H plus ion is going to be calculated really from the original amount of HA. You consider all the moles of HA to be turned into H plus and A minus. So if you had 2 moles per liter of HA, at equilibrium you'll have 2 moles per liter of H plus and 2 moles per liter of A minus, and no HA left over if you're a strong acid. In the case of a weak acid, your HA is going to be mostly what you started with, and you'll have just a tiny bit of H plus, much less than the amount of HA that you had originally. As far as the conjugate base is concerned, for a strong acid, the conjugate base is much weaker than the base water, much weaker of a base than water. For a weak acid, the conjugate base is a stronger base than water. It's a stronger base, meaning it's better at taking H pluses away than water is. This would be molecule pictures of some strong acids, sulfuric, perchloric, nitric. Those were on our list of strong acids. notice that the hydrogens, the little blue things, are attached to the red oxygens. So in these acids, the OH polar bond, is the one that is going to be broken to make H+. Here's some weak acids: phosphoric, nitrous, and hypochlorous acid, HOCl. Remember, if you're not one of the 6 strong acids, you're one of the weak ones. These also show oxygen being the atom on the molecule that the H attaches to. So, for example, H3PO4, H is written next to P in the formula, but in the molecule itself, H is actually attached at the oxygens. We call that oxyacids. I believe it was Antoine Lavoisier that theorized that to be an acid, you had to have a molecule containing oxygen. It's not quite true. There are examples of acids that do not have oxygen, but many of our acids do have oxygen, and they're called oxyacids. And typically your acidic proton, your H+ that's going to be removed, is going to be starting on the oxyacid at the oxygen atom. So these can be strong or weak, as we saw in the previous 2 slides. Oxyacids can be strong, sulfuric perchloric nitric, or weak, phosphoric nitrous hypochlorous. Organic acids are sort of its own subset of oxyacids. You start with some kind of carbon backbone. That's what makes it an organic molecule. But then somewhere on that carbon backbone, you have a double bonded oxygen on a carbon and also an OH group on the same carbon. This combination makes that OH one where the H can come off as H+. These are going to be weak acids. None of the examples of strong acids are organic acids. This particular functional group in the organic topic is considered the carboxyl group. So it has a name. It's called the carboxyl group. It's when you have carbon double bonded to oxygen, single bonded to OH. You also have your hydrohalic acids: HCl, HBr, HF, HI. These are all examples of the hydrohalic. And 3 out of the 4 are strong acids: HCl, HBr, and HI. HF is considered weak. The bond is a little too strong to break 100% of the molecules up. Typically we say these are HX, and X is the halogen atom. Here we see the organic acid, the black being carbon, the red being oxygen. So you can see acetic acid has a carbon with a double bonded oxygen and a single bonded OH. And the acidic hydrogen is not the H's on the carbon, but the H on the O, the H attached to the O. Benzoic acid has a benzene ring, which is your 6 carbons in a ring there, in a hexagon. And then you have a C attached to that benzene ring with a double bonded oxygen and a single bonded OH. It's the H on the oxygen that is your acidic hydrogen. The H's attached to carbon are not polar and are not able to be pulled off by water to make H+. So here we have a table of some weak acids and their Ka values. Sulfuric acid, H2SO4, is strong, but after losing H+, it forms the hydrogen sulfate ion, HSO4-, which actually has the ability to lose another H+, so it could lose even a second H+. However, the second H+ is not considered strong. The Ka value, or the ratio of H+ and A- to HA, is 1.2 times 10 to the minus 2, which is approximately 1%. So 1% H+ and A- and 99% HA. I'm playing fast and loose with the math there, but you can see the Ka value there is a small number, 1.2 times 10 minus 2. Chlorous acid, virtually the same strength. HClO2 breaks up into H+ and ClO2- with a Ka of 1.2 times 10 minus 2. But as Ka values go, 1.2 times 10 minus 2 is actually fairly large compared to a lot of other weak acids, which are much weaker even yet. monochloroacetic, 1.35 times 10 minus 3. You can see the list yourself. But generally, as we go from a larger Ka, 10 to the minus 2, to a smaller Ka, for example, phenol, 10 to the minus 10, what we're doing is our equilibrium is lying less and less to the right. We're getting a smaller Ka, meaning less to the right. In other words, less H plus and more molecules hanging together and not losing H plus. More HA, less H plus on the right there. So for practice here, let's practice by trying to arrange 5 things according to their strength as bases. So we have water F minus. F minus is a conjugate base of HF, which we see in this chart. HF is hydrofluoric acid, 7.2 times 10 minus 4. We have Cl minus, which is the conjugate base of HCl. It's not in this chart because it's a strong acid. It's got a very large Ka. We have NO2 minus, HNO2 nitrous acid, 4.0 times 10 minus 4 for Ka. And Cn minus, cyanide, hydrocyanic acid, HCN, has a Ka of 6.2 times 10 minus 10. So first of all, we would pick out that water is a pretty weak base, but the only thing weaker than water is the conjugate base of a strong acid. So Cl minus is actually the weakest base in this list. And then water would come in next. Then we would have all those conjugate bases, F minus, NO2 minus, and Cl minus. The conjugate bases of the weak acids in this list here, HF, HNO2, and HCN. So now, how do we list them in order? They're stronger bases than water, but how do we list the order of them from weakest to strongest? Well, the general principle is the strength of an acid is inversely related to the strength of its conjugate base. So, since HF is the strongest of the weak acids, 7.2 times 10 minus 4, we would say F minus is the weakest of the conjugate bases. HNO2 is the next strongest, so NO2 minus is the next weakest base. And then hydrocyanic acid is actually very weak, meaning HCN doesn't want to give up H+, so Cn minus would very strongly want to gain H+. So that puts our order as F minus is a weaker base than NO2 minus, which is a weaker base than Cn minus. So combining everything together, we have Cl minus is the weakest base because it's the conjugate base of a strong acid. Water is next. Fluoride is next because of the weak acids listed, HF and HNO2 and HCN, HF is the strongest of those weak acids, so its base is the weakest of the three, then NO2 minus, then Cn minus. So that's a way to kind of analyze the tendency of an ion or water to take H plus away from something. How good of a base is it? Water, in fact, we normally think of water as neutral, but if we look at it from the perspective of the Bronsted-Lowry model, water is actually able to behave as either an acid or a base, and it's not the only thing that can do that. If we think of it, water as an acid would be donating H plus and becoming OH minus. Water as a base, it would be accepting H plus and becoming H3O plus or hydronium. See, water can do both. It can give H plus away or accept H plus. So we have a term for that. When a molecule or ion can either donate or accept H plus, we call it amphoteric. Just means that it's got that double ability to either be an acid or a base. Now, in fact, water will interact with water in pure water, and there will be a very few number of ions that actually form because one water will act as an acid and take H plus away from another water, which will be acting as a base. We call this the autoionization of water or the self-ionization of water. At 25 Celsius in pure water, you'll actually have, the H2O molecule ionizing itself, autoionizing, will actually have in pure water an H plus ion concentration of 1 times 10 to the minus 7 molar. But because every time you take H plus off of water, you get OH minus, you'll also have a concentration of hydroxide of 1 times 10 to the minus 7 mole per liter. So in fact, being neutral doesn't mean not having any H plus or any OH minus at all. Being neutral simply means having an equal amount of H plus and OH minus. If we look at the reaction, H2O yields H plus plus OH minus, the K for that we're going to call KW. And the KW is going to be H plus times OH minus, and we won't divide by water because it's a liquid, or 1 times 10 to the minus 7 times 1 times 10 to the minus 7. So this K is very tiny. KW is very tiny. It doesn't ionize a lot, but it does have a value of 1 times 10 to the minus 14. This is a very important reaction because a lot of our acid-base reactions occur in water. So we have to remind ourselves that water is doing this ionization equilibrium. Even as acids and bases are doing their own equilibria, you also have the water doing its equilibrium. So with that in mind, since Kw equals H plus times OH minus and it equals 1 times 10 minus 14, there's a relationship between H plus and OH minus. No matter what is in water, the H plus times the OH minus, the product of H plus and OH minus molarities, has to equal 1 times 10 to the minus 14 because that's the equilibrium constant. So when you have a neutral solution, your H plus and your OH minus are equal. At 25 Celsius, that means they'll be 1 times 10 to the minus 7. In an acidic solution, you're going to have more H pluses than OH minuses. Doesn't mean you won't have any OH minuses, you'll just have more H pluses than OH minuses. But the H plus times the OH minus will still equal 10 to the minus 14. So looking at the diagram, let's say we have an acidic solution and our H plus is 10 to the minus 4 moles per liter. That means our OH minus is 10 to the minus 10 because they have to multiply to give 10 to the minus 14. In a basic solution just means you have more OH minus than H plus. So if your OH minus were 10 to the minus 14, that means your H plus would be 10 to the minus 10. Now this is actually the equilibrium that the whole pH scale is based on. Notice when the H plus is 10 to the minus 7, you have a pH of 7. When your H plus is 10 to the minus 4 moles per liter, you have a pH of 4. If your H plus is 10 to the 0, or in other words, you have H plus ion molarity of 1, your pH is 0. 10 to the 0, 0. If your H plus, if you're in a base and your H plus is all the way down to 10 to the minus 10, because your OH minus is 10 to the minus 4, then your pH is 10. So the pH scale is actually based on the molarity of H plus, and particularly it's the exponent. And we'll see that in a few here. So what is the equilibrium constant expression for an acid acting in water? So let's remind ourselves, acid in water, HA generically, acid in water, makes H3O plus plus A minus, so the equilibrium constant expression would be Ka equals H3O plus times A minus over HA, or if you want to shorten it down, H plus times A minus over HA, and usually we do want to shorten it. If the equilibrium lies far to the right, what kind of value are we going to have for Ka? Well, if the equilibrium lies far to the right, we're going to have a lot of H3O plus and a lot of A minus. We're going to have a big numerator and a small denominator. Very little left over HA. So that means if you have a big numerator and a small denominator, your Ka is going to be large. If the equilibrium lies to the left, Ka is going to be small or less than 1. If water is a better base than A minus, so let's look at it. Water on the left trying to take H plus away from HA, A minus on the right trying to take H plus away from H3O plus. If water is better at taking away H plus, this equilibrium is actually going to lie to the right. The products are going to dominate. The forward reaction is going to be more dominant than the reverse reaction. So in that case, we would say HA is a strong acid because it gives up H plus easily to water. And then the A minus doesn't try to take it back very strongly. So that would mean our Ka, since it lies to the right, would be greater than 1. So the products would dominate. We'd have a strong acid, Ka greater than 1. Let's look at a 1 molar solution of HCl. We have water in there. We have Cl minus in there. And let's compare to A minus, the ion from some generic weak acid, HA. Let's order our bases from strong to weak. So remember, water is sort of caught between the conjugate base of a weak acid, which is stronger than water, and the conjugate base of a strong acid, which is weaker than water. So from strong to weak, it's going to be A minus, because HA is so reluctant at giving up a proton. A minus would be very strongly motivated to get a proton. Water is right there in the middle, and then Cl minus, because HCl easily gives up a proton, Cl minus does not want to take it back. So to be a base means you want to take a proton, take an H plus. So you can actually get a base by dissolving a salt with a sodium ion and A minus, the anion from a weak acid. Let's say you've got the weak acid HF. NaF would put F minus in the water, and the F minus ion could take H plus from water. Water would then act as an acid and make HA and OH minus. So that's how it would be making a base. So HA is a weak acid, A minus is its conjugate base. So if you just put A minus in the water, maybe bring it in as part of a salt like sodium A minus, that could actually create a base. This equilibrium would lie to the left because it would be a weak base, not a strong base. Now, remember, we were talking earlier about A minus taking H plus from H3O plus. Now we got a little different situation here. The A minus is trying to take H plus away from water. It's much easier to take H plus from hydronium than it is from water. This would actually be a weak base, and the equilibrium would lie to the left. However, the weaker the acid, the stronger it is, even though it's still a weak base. So it's a little confusing. It's a weak base, but we're talking about relative strengths. The weaker the acid, the stronger its conjugate base, even though the conjugate base is still considered a weak base. The Kb would be less than 1. So in this case, we were talking about the Kb, meaning the equilibrium constant for a base. So since the equilibrium lies to the left, the K for this equilibrium would be less than 1. We would consider A minus a weak base. The conjugate base of a strong acid is virtually neutral. The conjugate base of a weak acid is a weak base. The weaker the acid, the stronger the weak base is. Acetic acid and HCN are both hydrocyanic, are both weak acids, but acetic acid is stronger than HCN. So now let's try to order these from weak to strong. So we've got water in there. It's going to be somewhere in the middle. We got Cl minus, the conjugate base of a strong acid. That's going to be the weakest of all. Then we have cyanide and acetate, Cn minus and C2H2O2 minus. These are the conjugate bases of the two acids, HCN and HC2H2O2. Since acetic acid is stronger as an acid than HCN, it's going to be weaker as a base for the acetate ion C2H2O2 minus. So our order is Cl minus is the weakest because HCl is the strongest acid. H2O is in the middle. And then we have our two conjugate bases of weak acids, but the stronger the acid, the weaker the base, so it would be acetate first, then cyanide last. Okay, so let's take a look at a reaction between a weak acid and some other molecule's conjugate base, HCN and F minus, making CN minus NHF. So we have the weak acid HCN, we have the conjugate base F minus, we have CN minus, the conjugate base of HCN, and we have HF, the conjugate acid of F minus. Now here we see the competition is, H plus is like a hot potato. Who wants it? Does HCN prefer to have the H plus, or does F minus prefer to have the H plus and be HF? Well, if we look at Ka, the Ka for HCN is 6.2 times 10 minus 10. That's a very small number. The Ka for HF is 7.2 times 10 minus 4. So it looks like HF is better at giving away H plus than HCN is. And so HCN is trying to give the H plus away going to the right. HF is giving away the H plus going to the left. HF has a bigger Ka, so we say HF is better at giving away H plus, and so this equilibrium is going to lie to the left, and having fewer products, the K is going to be less than 1. Now we can actually calculate that. Let's show you how we could calculate the K value. We have the reaction, and we have the Ka for HCN and the Ka for HF. We could look at this as the HCN reaction going to the right with a K of 6.2 times 10 minus 10, but then we flip the K, or we flip the reaction for HF. Instead of saying HF yields H plus plus F minus, Ka equals 7.2 times 10 minus 4, we flip it and we say, well, let's make the reactants of products. F minus plus H plus yields HF. So now since we flipped it, we take the reciprocal of Ka, 1 over 7.2 times 10 minus 4, which comes out to 1.4 times 10 to the third. Now if we look at that, we cross out the H pluses, add those two together, we get that reaction. HCN plus F minus yields CN minus plus HF. If you add two reactions to get another reaction, you multiply their Ks. So we take the first K, 6.2 times 10 minus 10, times the second K, 1.4 times 10 to the third. You get the K for this reaction is 8.7 times 10 minus 7, which reinforces our previous conclusion that the K would be much less than 1 because it would prefer to lie to the left and not go to the right when it reaches equilibrium. All right, let's go back to that KW example and let's calculate some H pluses and some OH minuses depending on some certain information that we have. And then we're going to state whether the solution is considered to be neutral, acidic, or basic. Let's start with a 1 times 10 to the minus 5 molar OH minus. Let's find the H plus molarity. So the relationship was Kw was H plus times OH minus, and that equaled 1 times 10 minus 14. If we plug in 1 times 10 minus 5 molar for the OH minus, then we divide both sides by that, we get 1 times 10 minus 14 divided by 1 times 10 minus 5, and we get the H plus is 1 times 10 to the minus 9. Since our H plus is 10 to the minus 9 and our OH minus is 10 to the minus 5, we have a bigger molarity of OH minus than H plus, so we would call that solution basic. Now here's a little interesting relationship. At 60 Celsius, remember Kw that we had previously, 1 times 10 minus 14, is based on 25 degrees Celsius room temperature. But if you warm water up, the Kw changes from 1 times 10 minus 14 to 1 times 10 minus 13. So let's remind ourselves about Le Chatelier's principle in chapter 12 and predict whether this reaction of water ionizing to make H plus and OH minus is exothermic or endothermic. And part B, let's calculate how much H plus and OH minus neutral water would have at 60 Celsius. First of all, we see that the K increased from 1 times 10 minus 14 at 25 Celsius to 1 times 10 minus 13 at 60 Celsius. So Le Chatelier's principle would say if a system at equilibrium is heated, then it's going to consume energy. Energy is on the left. It's endothermic if it pushes that equilibrium to the right when it's heated. So we're actually looking at this as the K increases with temperature, meaning the equilibrium shifts to the right when you raise the temperature. So we have to look at this as an example of energy as a reactant. So the process is endothermic. So I can tell by how the K changes at different temperatures whether the process is endothermic or exothermic. And then to do this part B, at 60 Celsius, neutral water would still be neutral, so the H plus will still equal the OH minus, and the H plus times the OH minus at 60 Celsius is 1 times 10 to the minus 13. So if the H plus equals the OH minus in neutral solution, then the H plus and the OH minus are both going to equal the square root of 1 times 10 minus 13, which is 3 times 10 minus 7. There's 3 times as much H plus in water at 60 Celsius than there is at 25 Celsius. 25 Celsius, it was 1 times 10 minus 7 molar. Also 3 times as much OH minus. Which brings us to the pH scale. The pH scale, you may have heard of pH before. It's sort of a way of ranking how acidic or how basic something is. It's a scale, but it's a more compact way. Instead of dealing with all these scientific notation numbers, we actually sort of shorten them down by taking their logarithm. If you take the log of something, if you take a log of 10 to some power, if you take the log base 10 of that, you get the power as your number. So for example, the log base 10 of 10 to the third is just 3. And so it's a way of sort of shortening it down. Instead of having to write out 1 times 10 minus 7, you could just say minus 7 would be the logarithm of that. Now, in fact, pH is not just the logarithm, it's the negative of the logarithm. And this makes pH a logarithmic scale, kind of like the earthquake scale, the Richter scale. Every number then is a power of 10. If you have an earthquake of 6, that's 10 times stronger than an earthquake of 5. And an earthquake of 7 is 10 times stronger than an earthquake of 6. So in a similar way, every one number on the pH scale is actually a power of 10 difference in the molarity of H+. But unlike the Richter scale, where bigger numbers are stronger earthquakes, pH actually gets smaller as H plus increases because we're taking the negative log of the H plus molarity. So if you have a solution, say pure water at 25 Celsius, and your molarity of H plus is 1 times 10 minus 7 molar, the log of that is negative 7, and the negative log of that is just 7. So neutral water has a pH of 7. Meaning the molarity of H plus in neutral water is 1 times 10 to the minus 7. However many decimal places you have in the pH should match the number of significant figures in your molarity. So if your molarity has 2 significant figures, you should show 2 decimal places in your pH. So if your H plus is 1.0 times 10 minus 9 molar, your pH should be 9.00 because 1.0 had 2 sig figs. You should show 2 decimal places in your pH. Log scales can also be used for other things besides pH. They can be used for representing the molarity of OH minus. The negative log of OH minus is POH. or you could use it to represent the logarithm of your K value, your equilibrium constant. pK would be negative log of K. We'll use that in a few minutes. So the pH range, pH 7 is neutral, pH greater than 7 is actually higher pH would be more basic. pH less than 7, lower pH is more acidic, and that's because we're taking the negative of the log. So some common things and their pHs. 1 molar NaOH has a pH of 14, ammonia has a pH of 12, baking soda somewhere between 8 and 9, your blood is actually slightly over 7, pure water is 7, so everything above pure water on this diagram would be basic. Milk is slightly acidic, slightly less than 7. Black coffee is a little more acidic, about 5. Vinegar is 3. Lemon juice is even lower. Stomach acid is about 2. Battery acid is about 1. 1 mole per liter HCl is about 0. It's a common misconception that the pH scale starts and begins at 0 and 14. Actually, if you have a molarity greater than 1 molar, for a strong base like NaOH, it can actually go above 14. Or you could even go below 0 if you have a more concentrated acid. So the pH range does not just go from 0 to 14. It can go above 14 or below 14 for very concentrated solutions. Let's practice calculating some pHs, and for the fun of it, let's go ahead and also calculate some pOHs. And these would be solutions at 25 Celsius. First one we'll do is 1 times 10 to the minus 3 moles per liter of OH minus. And then we'll also try 1 mole per liter of OH minus. So starting with the 1 times 10 to the minus 3, H plus times OH minus equals Kw, or H plus equals Kw divided by OH minus. The Kw is 1 times 10 minus 14, the OH minus is 1 times 10 minus 3, so the H plus is 1 times 10 minus 11. Take the negative log of the H plus, and you get 11.00. The pH would be 11.00. The pOH would actually just be the negative log of OH minus, and we're already told that that was 1 times 10 minus 3, so the negative log of 10 to the minus 3 would just be 3.00. So for this solution, where the molarity of OH minus is 1 times 10 minus 3, the pH is 11, and the pOH is 3. Now, the second one was I think this is a misprint here. Let me real quickly fix this. Let's make this 1 molar H plus, looks like. Okay, so my second problem is 1 mole per liter of H plus, I believe. So, no, the mistake is not there. Let me go back here. Sorry about this. I should have caught this mistake. This is in fact OH minus. The mistake is in the way they solve it, not in the way they presented the question. All right, so here we go, back to here, back to this slide. They put H plus and OH minus in the wrong place here. See, the OH minus here and the H plus here, they should have put the OH minus down below Kw because it was 1 molar, and then this should be the H plus on the left. So there's a mistake in this solution. I can't edit this because it's a picture, not a text. So when I will edit it before I print these notes out and give them to you on Tuesday, I'll fix this. But imagine that this here, where it says OH minus equals Kw over H plus, it actually should say H plus equals Kw over OH minus. So Kw, 1 times 10 minus 14, OH minus 1 mole per liter, So the H plus is going to be 1 times 10 minus 14. So your pH, back up the bus. Looks like I spoke too soon. Looks like they did mean this to read. Sorry about the confusion here, but trying to redo this video is just going to take too long, so I'm going to go ahead and say that they meant letter B to be presented as 1 molar H plus. So then the solution to the problem would be that the OH minus is 1 times 10 minus 14 divided by 1 times 10 minus 14. The pH is a negative log of 1 mole per liter of H plus, or 0. The log of 0 is 0, or log of 1 is 0. And then the pOH would be the negative log of 1 times 10 minus 14, so it would be 14. Okay, sorry about the confusion there. The confusion got in there because the way the problem was presented wrong. It should have been 1 mole per liter H plus, not 1 mole per liter OH minus. If you take the problem as being 1 mole per liter H plus, this solution works. Now, I just want to point out something about these two solutions. First of all, the first example, pH was 11, pOH was 3. In the second example, pH was 0, pOH was 14. You're probably noticing a pattern there. The pH and the pOH actually add up to 14 at 25 Celsius. And that's because Kw is H plus times OH minus. If you take the log of both sides, log of Kw, you get the log of H plus the log of OH minus. Or if you take both sides times -1, you get negative log of Kw equals negative log of H plus minus log of OH minus, or pKw equals pH plus pOH. Well, pH plus pOH is 14 because the negative log of Kw, 10 minus 14, is 14. So there's a relationship that's kind of handy to know. If you know the pH, the pOH is just 14 minus the pH, and vice versa. So the pH of a sample of human blood was measured to be 7.41. Find the pOH. Well, the pOH is just 14 minus the pH, or 14 minus 7.41, 6.59. Now let's find the H plus and the OH minus. Well, now we're actually going backwards. Instead of having the H plus and finding the pH by taking the log, we're actually trying to find the H plus from the pH. So if our pH is 7.41, and that equals the negative log of H plus, or in other words, the log of H plus equals negative 7.41, then I need to take the anti-log. To get rid of a logarithm, you have to take the anti-log. The anti-log for log base 10 is just 10 to the x, or 10 to the n here. So in our case, the H plus is going to be 10 to the minus 7.41 rather. 10 to the minus 7.41, which if you plug in your calculator is 3.9 times 10 minus 8. The OH minus is going to be the anti-log of the negative of the pOH. So it's an anti-log of negative 6.59, or 10 to the power negative 6.59. 2.6 times 10 minus 7. You could check yourself because 3.9 times 10 minus 8 times 2.6 times 10 minus 7 should equal 1 times 10 minus 14. So section 13.4, we're going to find some pHs of some strong acid solutions. So when you're solving acid-base problems and they ask you to solve for a pH or solve for an H plus ion concentration, you want to think about the chemistry going on. Focus on what is in the solution. Did you put an acid in the solution? Did you put a base in the solution? If you did, what is the Ka of that acid? What is the Kb of that base? And you want to kind of walk your way through these. But you do want to be flexible. It is a step-by-step approach, but you do need to be flexible and keep your eye on the big picture as you're working out the problems, because they can switch things up in the problems so that you don't always solve them exactly the same way every time. So it's better to kind of problem solve from a big picture perspective than rather narrow yourself down and just try to do a step-by-step thing and follow a recipe, so to speak, or an algorithm. You want to break the problem into workable steps and then make sure you understand the problem as well as you can, because often then the problem will guide you to your solution. So this is me always saying, read the question, read the question, read the question. The better you understand what's being asked, the better you can be guided to how to solve that problem. So the point is, you should be understanding what you're doing, not just blindly working a set of steps to hopefully get the right answer. And in finding pH or working an acid-base problem, you're going to want to know, what are my major species? What has the greatest concentrations in this solution? And then what is my dominant reaction? Is it the reaction of water ionizing to H plus and OH minus? Is it some other equilibrium? Is it some reaction that's not even equilibrium? It goes all the way. For example, pH of strong acids, you don't even work it out as an equilibrium problem. You think of strong acids as ionizing completely. Once you focus on your major species, then you can understand a little bit of what is my concentrations for each of the species, and that should hopefully guide you to your pH. So let's look. Let's say we have a solution that's 2 times 10 to the minus 3 moles per liter HCl. What would be my major species? Well, my major species would be H plus and Cl minus and water, because you put HCl in water, it ionizes completely to H plus and Cl minus, and there aren't any HCl's left over. Now, what would be the pH? Well, the pH would be determined from the H plus. 2 times 10 to the minus 3 moles per liter of HCl is going to totally ionize and give you 2 times 10 to the minus 3 moles per liter of H plus. And that's lots more than you'd ever expect to get from water. Remember, when water ionizes, it only gives 1 times 10 to the minus 7. So HCl is your best source of H plus, and it's giving you 2 times 10 to the minus 3 moles per liter. And so that is going to be what you use to find your pH, the negative log of 2 times 10 to the minus 3. Put in your calculator, you get 2.70. So that would be an acidic solution, a pH less than 7. And that's because your strong acid, even though it was fairly dilute, 2 times 10 to the minus 3 molar, it did give you quite a bit of H plus. So here's a summary of the 2 parts to that question. Let's do another one. Find the pH of 1.5 times 10 to the minus 11 molar HCl. Again, HCl is a strong acid, but it's only going to be giving you 1.5 times 10 to the minus 11 moles per liter. You actually get quite a bit more than that from just pure water. Pure water gives you an H plus ion concentration of 1 times 10 to the minus 7. Which is like 4 powers of 10 greater than 1.5 times 10 to the minus 11. So actually, in this case, the water is the better source of H plus than the HCl, and so your pH is going to be 7. It's the H plus from the water that determines the pH, not from the HCl, because the HCl is just too dilute, 10 to the minus 11. Here's another strong acid, HNO3. We can consider it to be 100% ionized. Let's find the pH if you have 1.5 times 10 to the minus 2 moles per liter of HNO3. Being a strong acid, the equilibrium lies all the way to the right, H plus and NO3 minus. So since your HNO3 was at 1.5 times 10 minus 2, now your H plus is going to be 1.5 times 10 minus 2. That's a lot more than water gives you, so your pH is the negative log of 1.5 times 10 minus 2, or 1.82. Again, I'm going to try to trick you with the classic, let's find the pH of 1 times 10 minus 10 moles per liter HCl. You're like, okay, 10 minus 10, pH is going to be 10, but that would actually be a base, and you would not expect HCl, an acid, to give you a base. So H plus, Cl minus, and water are your major species, but the H plus from the HCl is a lot smaller than the H plus from the water. So actually, you're going to be the pH of pure water because the HCl is just too dilute to affect the pH. So you're back to that pH of 7. All right, so I believe that takes us to 13.5, which we will pick up at 13.5 on Tuesday of next week. We'll also take our test on Tuesday of next week. So start out the day, Tuesday of next week, with the test. Then I will have time for questions on 13.1 through 13.4. I went through it fairly quickly, but that would actually give you time if you want to listen to this more than once. You could listen to this video more than once. But I'm guessing you're going to have questions because I threw a lot of math at you. pH, negative logs, and all that stuff. You're going to have questions about that math. So after we have our test, I'll take questions and whatever it takes to get all your questions answered about 13.1 through 13.4. I suggest as you watch the videos to read the chapter and also take notes and write down what you want to ask me questions about. You can also email me questions if you don't want to ask them in class. But just work on 13.1 through 13.4. Try to get your brain wrapped around what is an acid, what is a Bronsted-Lowry acid, what is a Bronsted-Lowry base, what's a conjugate acid, what's a conjugate base, how do acids affect pH, and how is pH calculated, and all that stuff. And we'll get those questions answered, then we'll move into 13.5. But I realize not meeting in person, not being able to stop me and ask me questions in class, that makes a difference. And so I want to present an opportunity for you on Tuesday after the test over 11 and 12. I'll give you a chance to answer questions on 13.1 through 13.4. All right, with that being said, keep an eye on Canvas for some homework questions to be signed, and I'm going to email out to you all a link to this video so you can watch it. Thank you very much.